A company that manufactures pet toys calculates that its cost and revenue can be modeled by the equations given in the problem, where X is the number of toys produced in 1 week. Production during one particular week is 5,000 toys and is increasing at a rate of 350 toys per week. Find the rate at which the cost, revenue, and profit are changing. Because the X variable represents a number of toys, and that also fluctuates over time, your cost, revenue, and profit will also fluctuate with time. If you look at your cost function, you have 30,000 plus 1.35x. 30,000 is a constant, its derivative is 0, but 1.35x contains a variable. Now, because that variable x also changes with time, your change in cost over time will involve a production level change over time. So long story short, with a related rate, when you take a derivative, if your term contains a variable, you take the derivative like you normally would. For example, 30,000 goes to 0, 1.35x would be 1.35. But if your term contains a variable, even if it goes away during the derivative, you still have to account for that variable's change over time. So that represents a term called dx over dt. That's the change in production over time. Now we're given that value in our problem. 350 toys per week is the rate at which production is increasing. So that's going to influence our cost. 1.35 times the rate of change in production is going to give us a total change in cost over time of $472.50 per week. These derivatives are a little bit harder to take because you have two variables and they both change with time. Your revenue function, 500x minus x squared over 25, both terms have a variable. The first term, 500x, its derivative would be 500. But because the x variable changes with time, we have to write in dx dt. Even though the x went away, you still have to account for its change over time. Your second term, negative x squared over 25, its derivative is negative 2 over 25. The x squared turns into an x. But again, this term has an x variable, and that variable changes over time as well. Back in the description of the problem, the production during one particular week is 5,000 toys. That's your x value. Increasing at a rate of 350 toys per week, that's your dx dt. Substituting in 500 times 350 minus 2 over 25, 5,000 times 350 that's equal to 175,000 minus 140,000 which gives us a change in revenue of $35,000 per week. Since profit is equal to revenue minus cost, the change in profit is equal to the change in revenue minus the change in cost. And since we've already taken both of those derivatives, we're not going to let our hard work go to waste. Okay, so I'm going to bring this over. DRDT was 500 dx dt minus 2 over 25x dx dt. Minus 2 over 25 x dt, dx dt. Okay, so that's the change in revenue minus change in cost was 1.35 dx dt. Now we've already plugged these values into parts A and B. The revenue from part B was a change in $35,000 per week. The change in cost from part A was $472.50 per week, for a difference of, or a change in profit of, $34,000 $527.50 per week. There's always that underlying time variable. The profit P from selling X units of a product is given by the equation. The sales are increasing at a rate of 6 units per day. Find the rate of change in the profit in dollars per day when X is equal to 200 units and when X is equal to 300 units. First, let's get the change in profit over time. X is the number of units that also changes over time. So like the first example, we've got to be mindful when we take the derivative that the change in profit over time will contain the X variable and the rate of change of X over time. 560X has a derivative of 560. Because it contains a variable that changes over time, don't forget dx dt. 0.4x squared has a derivative of 0.8x, but that x variable changes over time. Basically, it's derivatives like we've been taking. It's just if that variable also changes over time, not to forget dx dt. if X is your variable. The sales are increasing at a rate of 6 units per day. That's our dxdt value. In part A, X is 200. So let's make some calculations. 560 times 6 minus the back half, if you're careful with your calculator, I believe that comes out to 960, giving us a change of profit of $2,400 per day. Part B, all the hard work was done in Part A. Change in profit over time. And we'll just go ahead and substitute 300 in for X, where on Part A we subbed a 200 in. 560 times 6, that stays the same. Minus 0.8, change to 300 times 6. Alright, so that's still 3360. The back half changes a little bit. I think that multiplies out to, if I did it right, 1440, giving us a change in profit of 1920 per day. A retail sporting goods store estimates that the weekly sales and weekly advertising costs are related by the equation given. The current weekly advertising costs are $1,900, and these costs are increasing at a rate of $125 per week. Find the current rate of change of the weekly sales with respect to time. Okay, so change in sales with respect to time. 2230 from the original equation has a derivative of 0, and there's no x attached, so we don't have to do a dx dt. The second term, 60x, has a derivative of 60. It does have a variable, so we will have dx dt. Third term, that derivative, 0.35 times 2 is 0.70, or you can simply write 0.7x, and then don't forget dx dt. Increasing cost at a rate of 125 per week, that's our dx dt. X is 1900. I kind of painted myself in a corner here. Still times 125 for the dx dt. 60 times 125, that's 7,500. Plus 0.7 times 1900 times 125, that's 166,250 for a grand total of $173,750 per week. Hope this helps.